Hello, welcome to the 2018 AIME I class, and so today we're gonna start from number 5. Please hold on for a second. Okay, sorry. So, yeah, and so I'll give you a couple of minutes to try each of the problems on your own before I go over the problems. Okay, so I guess I'll start going over this problem now. So, in the problem, you have that for each ordered pair of real numbers x and y, such that log base 2 of 2x plus y equals log base 4 of x squared plus xy plus 7y squared, there is a real k such that log base 3 of 3x plus y equals log base 9 of 3x squared plus 4xy plus ky squared. And so something important that we should see is if we look at the bases, the one on the right is always the square of the number on the left. And so, first of all, we can use the fact that log base a to the power of n of b to the n is just equal to log base a of b. And so what that tells us is that for here, it tells us that 2x plus y squared is equal to x squared plus xy plus 7y squared. And so we're already given this, so then we can just expand this out. So 4x squared plus 4xy plus y squared equals x squared plus xy plus 7y squared. And now we can move everything from the right to the left side. And so what that leaves us with is 3 times x squared plus xy minus 2y squared is equal to 0. And we can factor this if we want. And if we factor, what that tells us is that x plus 2y times x minus y is equal to 0. And so this means that x equals negative 2y or x equals y. Okay. And so after this, now we can do the same thing here. And so what the second equation tells us is that 9x squared plus 6xy plus y squared, because this is 3x plus y squared, is equal to 3x squared plus 4xy plus ky squared. And now we have two cases, which is x equals y or x equals negative 2y. And if we put in x equals y, then we have that 9 plus 6 plus 1 is equal x squared times 9 plus 6 plus 1 is equal to x squared times 3 plus 4 plus k. And so k is equal to 9. And if x is equal to negative 2y, then when you plug that into here, what that eventually tells you is that k is equal to 21. And so you want to find the product of all possible values of k. And so there's two values of k, 21 and 9. And so the answer is 21 times 9, or 189. So does anyone have any questions about this problem? Okay, I guess not. And in that case, let's move on to the next question. Okay, so I'm going to start going over this. So let n be the number of complex numbers z such that the magnitude of z is equal to 1 and z to the 6 factorial minus z to the 5 factorial is real. And so you want to find the remainder when n is divided by 1000. And so clearly z to the 6 factorial minus z to the 5 factorial is just equal to z to the 720 minus z to the 120. And that's because these are the values of 6 factorial and 5 factorial. And so now you can substitute something in for z of 120 to make it easier. So we let a equal, sorry, not a, x equals z to the 120. And so now this problem basically is just x to the 6 minus x is real. And so this is true when the imaginary part of x to the 6 is equal to the imaginary part of x. And so we can let x equal e to the I theta. And so the imaginary part of 6 theta, e to the 6 I theta, is equal to the imaginary part of e to the I theta. And if we can just visualize just like increasing theta and then finding the value of 6 theta as a result, we can see that this has a total of 6 solutions every pi, or 180 degrees. And so that means there's a 12 solutions over the whole unit circle value of theta. And so that means that there's 12 solutions for the value of x. And for each of these 12 values of x, each of them is equal to x to the I theta. Sorry, each of these values of x is equal to z to the 120. And so that means that there's 120 values of z for every x. And so that just means that the number of complex numbers z that work is 12 times 120, or 1440. And this is equal to n. And since we want to find the remainder, but n is divided by 1000, it's just the last 3 digits, or 440. So does anyone have any questions about this problem?
Why are there 12 solutions for x?
Okay. So I guess you can just consider it like this. So in total, when 6 theta goes around 120 degrees, sorry, 360 degrees, theta will have gone around 6 times. And there's one solution for every pi for each rotation, and there's 6 rotations, so that's 12. Are there any other questions? Okay. If not, let's move on to the next question. Okay, so I'll start going over this now. So you have a right hexagonal prism, and it has a height 2. And the bases are regular hexagons, and they have side length of 1. And any 3 of the 12 vertices determine a triangle. And so you want to find the number of isosceles triangles that are formed, including equilaterals. So something important here is to note that the exact values of the side lengths don't really matter. What matters is the fact that the height is double the base, the side length of each of the bases. And so a diagram of this would look something like this. Okay, and it's a hexagon. And if we look at a regular hexagon with side length 1, then if we look at this is 1, this is 1, this is root 3 over 2, this is 1/2, and this is 1/2, and this is 1. And each of these exterior diagonals is, each of these long diagonals is length 2, which is equal to the height. And so for each, on each hexagonal surface, first of all, the first case is where the 3 points are on all on the hexagonal surface. And if this is true, it can be of the form this, or it can be an equilateral triangle. And for the form where it covers 2 sides and the diagonal that connects them, there's a total of 6 triangles of this kind, and there's also 2 equilateral triangles inside each hexagon. And so this is a total of 8. And there's 2 bases, so the total number of triangles on a base is 8 times 2, which is 16. And now if we look at the case where it all lies on a rectangle, this is impossible because none of the equal sides of them are connected to each other. And now the next case, you've already noted that this diagonal is of length 2, and that's equal to the height. And so the next case is when the triangle looks like this. The triangle is here. And in this case, there's 6 ways to rotate this. One for each which of the 6 that this side is on. And there's 2 ways to flip it around. Because this can either be rotated like this, or it could be like this. And so this is a total of 12 cases. And now, the final case is when the hexagon, the choices either look like
Wait. So for the 12 case, shouldn't you multiply by 2 again?
which one? There's basically 3 12 cases.
Oh, I'm talking about the one where it's a diameter of the hexagon and the height.
Okay. And so that's no, because basically you're choosing, there's 6 ways to choose this side. And once you've chosen this side, there's 2 ways to choose whether you're taking the diagonal across the top or the bottom. And once you do that, the 3 points have been determined. And so this it's just 6 times 2, which is 12. Okay, so does anyone have any other questions? Okay, I guess not. And in that case, let's move on to this question. Okay, well, I'll start going over this problem now. So let A, B, C, D, E, F be an equal angular hexagon such that AB is equal to 6, BC equals 8, CD equals 10, and DE is equal to 12. Okay. And so let D be the diameter of the largest circle that's in the hexagon. And so you're trying to find D squared. And so, first of all, we can draw a diagram. And so AB is equal to 6, actually. So first of all, an equiangular hexagon is basically achieved by cutting off edges, 3 equilateral triangles off of an equilateral triangle. And in this case, we can do something similar. So AB is equal to 6, BC is equal to 8, CD, that might be a bit off. Okay, C is here. Okay, CD is equal to 10, AB is 6, BC is 8, CD is 10, DE is 12, and so we want to find the remaining bits. And so just from this, the fact that these are equilateral triangles tells us that this is equal to 6, and this is 10, and this is 10. And so after that, this tells us that the sum of this length is equal to 24. And these add to 22, so this is 2, this is 2, and this is 2. And so this is 6, and so these add up to 8, and this is 24, so this is 16. And so to find the largest circle that fits inside, clearly it must be something that fits like this. A bit larger, but yeah. And so both of these lengths are equal to 14, and this is the diameter. And so if we look at it like this is 60 degrees, and this is 14, and this is the diameter. And so from this, we just have that D is equal to 7 root 3. And then so what that tells us now is that D squared is just technical difficulties, whatever. Okay, so D squared is equal to 149. So does anyone have any questions? Okay, I don't think there are, so let's move on. You can also clearly see that A is not equal to C. Otherwise, these would be equal. And so for each value of D, okay, so there's 17 values of D once you have chosen each value of 8B. Because once you choose the value of B, you've determined the value of A and C, and the possibilities for D can be anything other than those exact values. Because A and C are unique for a given B. And so that's 20 minus 3. And now for B, you can have B equals 6. B cannot equal 16, otherwise A is equal to 0, but there is no 0, so 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, and then 5, and then 4. Yeah. And so after this, you can't continue, otherwise C will be greater than 20. But however, we can also see that 8 and 12 are out of the picture because if B is equal to 8, then A is also equal to 8. And if B equals 12, then C also equals 12. And neither of these cases can happen. And so this leaves a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times 17 is 170. But in this case, there's also overlaps. And these overlaps are because, excuse me for a second. Sorry. And these overlaps are because of the values of D. And so Basically, they're because if we look here, then if we subtract them, we know that C minus A is equal to 8. But if we have that B minus D is also equal to 8, then this is a double counted set. And this is not good. And so if we do this, we have that from B equals 15, and then so 15, 14, 13, 11, 10, 9, 7, 6, 5, 4. And in this case, D would equal 7, 6, 5, 3, 2, 1, and these don't work. And so there's 6 values here that don't work. So 170 minus 6 is 164. And so the answer to this question are the sum of these two values, which is 164 plus 46, or 210. So does anyone have any questions about this problem?
On the right side, what does D refer to?
So basically, at
D
first,
refers to the since you have A and B being the two numbers that add to 16, C and D are the two numbers that add to 24.
no, that's
No,
the
I'm
left
talking
side
about
case.
the sharing.
In the right case, so basically we just let the four terms be A, B, C, and D in some order. And so D is the final term of the four element subset. Because in the equation you're given A, B, and C. But you have nothing dealing with D.
Okay, thanks.
Okay, so does anyone have any other questions? Okay. If not, let's move on to this question. Okay, so I'm going to start going over this problem now. So the wheel that's shown here is consisting of 2 circles and 5 spokes. And each point is labeled where a spoke meets the circle. Excuse me for a second. Okay, sorry. So a bug walks along the wheel and it starts at point 8. And for every step, the bug can walk from one labeled point to an adjacent point. And along the inner circle, the bug can only walk counterclockwise or in or outside. And along the outer circle, the bug can travel inside or it can travel clockwise. Okay. And so this is just an example path that's possible. And so we want to basically find the number of paths with 15 steps that both start and end at A. And we want to find the remainder ones divided by 1000. So we can we can basically define two variables O and I such that there are O moves that end on outside circle. And we let I be the number of moves that end on the inside circle. So now we can use the fact that it needs to start and end at A, sorry. And if we use this fact, this basically tells us that both O and I need to be multiples of 5. And so the first case is when O is equal to 15. And in this case, there's 0 values because clearly the final step must end at A, which is a circle, which is a point on the inner circle. And now the next case is when O equals 10 and I equals 5. And in this case, the end must be I or end in I. And so for the previous 14 terms, 4 of them must be I. And so that gives 14 choose 4 ways. And this is 14 times 13 times 12 times 11 over 24. And this is equal to 7 times 13 times 11. And that's basically 1001. And now, the next case is when O is equal to 5 and I is equal to 10. And in this case, once again, the final term is I. And all those terms, there's 14 terms, and 5 of them are O. And so this is 14 choose 5. And so this is equal to 14 times 13 times 12 times 11 times 10 over 120, which is 1001 times 10 over 5, or 2002. And the final case is when O equals 0 and I equals 15. And so there's clearly just one term because it's just 3 rotations of the circle. And so the answer here is just n is equal to 1 plus 2002 plus 1001, or 3004. And so we were trying to find the remainder when n is divided by 1000, so the answer is 004. Does anyone have any questions about this problem? Okay, well, in that case, let's move on to this question. Okay, so I'll start going over this problem now. So you want to find the least positive integer n, such that when 3 to the n is written in base 143, the two rightmost digits are 0 and 1 in that order. And so this is basically saying 3 to the n is congruent to 1 mod 143 squared. And so by the Chinese remainder theorem, you can split this up. First we can split 143 squared up into 11 squared and 13 squared. And so we're basically trying to find the smallest n such that 3 to the n is congruent to 1 mod 121, and 3 to the n is congruent to 1 mod 169. And so one way we can do this is to do these two cases separately. So first of all, 3 to the n is congruent to 1 mod 121. So 3 to the n mod 121, 3 to the 1 is 3, 3 squared is 9, 3 to the 4th, 3 to the cubed is 27, 3 to the 4th is 81, and then 3 to the 5th is 243, and mod 121 is 1. And then it repeats again. And so what this tells us is that 5 divides n. And that's all there is to this side. And for this side, we need to be a bit more careful. And so first we can do 3 to the n mod 13. And so with this, we have that 13, 3 is 3, 9, 3 squared is 9, 3 cubed is 27, mod 13 is 1. And then this just repeats again. So in order for it to be 1 mod 13, the first requirement is that 3 divides n. And so now we let n equal 3 and 1. And so now we have that 27 to the n1 is congruent to 1 mod 169. And so from here, we can just find that it's 27, 53, 79, 105, 131, 157, 14, 40, 66, 92, 118, 144, and then 1 again. And then 27, and again. So this tells us that 13 divides n1. And so when we put the fact that 5 divides n, 3 divides n, and 13 divides n, this tells us when n, we know that n is just needs to satisfy all of these. And so what this tells us is that the minimum value of n is 5 times 3 times 13, or 195. So does anyone have any questions about this problem?
So I suppose you first did mod 13 and not mod 169 was because there would be too many to bash out.
Yes.
Okay.
The reason I did 13 and then 169 is just to make it easier. But in the case of 11, it's really fast either way.
Okay. Because there would be like 39 before it repeats if you were just do 169, right?
Yeah.
Okay.
So does anyone else have any questions? Okay, guess not. So we can move on to the next question. This is 2 times 221. And now the other case is where A equals B equals, and the alternative case is when A equals B equals 6, 5, 4, 3, 2, 1, or 0. And in this case, there's only 1 because we cannot reverse the positions of A, B, and C, A or B. And so here we can apply van der Waals theorem. And so this is 12 to 6. And so this is this plus 12 to 6 to the 6 times this. And the denominator is clearly just 2 to the 18th because there's 2 to the 18th subsets. And so when we clear this out, this is 2 to the 12, 1366 divided by 2 to the 12 when we multiply it out. And this is equal to 683 divided by 2 to the 11. And since we wanted to find the value of m, we have that m is equal to 683. And so that's our answer. So does anyone have any questions?
Why do you have to multiply by 2 to the 6 at the end?
The reason is because this number here is just the number of ways to choose the ones and the negative ones. And the 2 to the 6 here is the number of ways to choose the zeros. Although in this problem, exactly, it doesn't really matter much because it still gets canceled out in the denominator, and the denominator basically just tells you that to cancel out all factors of 2 in the numerator. So are there any other questions? Okay, if not, let's move on to this question. Okay, so unfortunately there's not much time left, so I'll just quickly give us sketch. So you're given A, B, C, and your point X, and this is I1, and this is I2. And so first of all, you immediately know that this angle is just half of this angle, and you're given the side length of ABC, so you can calculate this angle. So to minimize the area, you're just trying to minimize I1, I2. And so from here, you can cleverly apply the law of sines to I1. And you can find AI1 equals something. And similarly, you can find that AI2 equals something. And so you can find an inequality from this. You can find an inequality off of the area of AI1, I2. And so after that, it should tell you that AX is a altitude. And so after this, you can use the fact that sine A over 2 equals the root of 1 minus cosine A over 2. And then you can find the area of A1, A2. AI1, I2, sorry. Yeah. And this is it for today's class. I'm sorry that I had to just quickly skim through the last solution. And yeah. So you can leave now if you want. If you have any questions, I guess you can ask more, but yeah.